Welcome everybody. This is the AGSA CERN panel follow-up from last year. We had a really good presentation from Dr. Padley and Dr. Eklund last fall, and we're doing it again because we'd like to hear about the latest developments going on at CERN and the science that's been done over the past year. So this panel is funded by Shell, the Shell fund is helping us eat and have a good talk. And we'd like to introduce Dr. Padley, Dr. Eklund, and have them tell us a little bit about what they're doing at CERN, and then we'll go from there.
Yeah, so I would start by saying the big change from a year ago is actually we're running and taking data and getting physics results out. So the accelerator started delivering colliding beams late March, and right now the first physics papers are being sent off to journals for publication. So you may have seen on the news in the past week there was actually the first thing seen that was not expected and was new. And I keep a Facebook page where you can actually go and see updates about what's happening. So we've been running and taking data. We've just gone through a technical stop, and they're firing up the machine to start physics right now. And you can go. You can always go online actually and see what the accelerator is doing. They've been on the web page, and they've just gone to stable beams, and so they're delivering. We're interested because we haven't had physics beams for a couple of weeks, and so Carl and I are all excited. And the luminosity is.
So that's how many collisions we get. Related to how many collisions we get every second.
So this is basically the current in the two machines.
You have to pour the other way.
The current in the two machines, and this is the energy. So we're running at 7 TeV center of mass right now. And this is a measure of the luminosity being delivered. That's on a very different time scale.
Actually, can you slide it over? I think the whole video is. There you go. So you can see it coming up. Yeah, that's a record right there.
So you've just witnessed the highest luminosity achieved at these energies in the history of humankind.
You can see what it was
just happened in the last few minutes.
All right.
So they're working to improve the performance of the beam all the time. They've had this long technical stop where they were doing lots of studies, and so it's come up more than it's ever come up before. Sorry, Carl and I are excited. Carl's worried that the pixel detector is tripping out as we speak. So when you go up in luminosity like that, sometimes it reveals problems with the experiment. So you want to add it?
Dr. Padley just mentioned that they just got things started again in basically the last 2 days. They've been running again after an extended period where they're trying to improve how much current they put in the beams. And if they continue on that path, we should get more, like a factor of 10 more beam intensity, not energy, just more collision in the next couple of weeks. So every day we run, we get a lot more data than on so-called on disk or on tape. So a lot of new things might get seen, and anything that looks interesting now, we'll be able to really check to see if it's real or if it was just luck that we got something fluctuated that looks like something interesting. So we're getting excited, I think.
Yeah, and so actually one of the things from the web displays, we use the web heavily to communicate with each other, figure out what's going on. So
this is what's called CMS TV. So we can go look at our experiment, and it shows the time at 7 hours later at CERN. So that's real time, pretty much. It tells what the machine is doing. Proton physics is stable. It tells us what run number we're at. They started at 100,000. So, and there it goes. It updates. It's like every 10 seconds or something. Maybe 30 seconds. It tells us how many events we record per second, or how many we read from the detector per second. That's only 1,000. I think we actually aren't seeing any collisions yet, even though the accelerator claims we are. Because that should be more like 100 kilohertz.
Did just drop the beam?
I'm not sure. Let's go back. So, usually when they first turn on it, they have to scan around to make sure the two beams actually are hitting each other. And there are 4 experiments, so they don't scan everybody at the same time or in the same order. We come back here. Yeah, it looks to me like we're not triggering very much.
Anyway, that might change.
As we watch that, it should go up. And there are all kinds of useful plots here, like we can see which of the detectors is on. They're all included in the run, the little green squares, and they're all running. Everybody's happy. And down here they show several different things, but in green it shows the trigger rate, which I would think should be higher. So we'll wait and see. And then the gray stuff is how many events have been recorded, which is written over here on this scale on the right side is the white line. So as we keep collecting data, that just increases. It's an integral, obviously. So anyway, we can kind of glance at this and see, oh, something's wrong. And like I would say, I think we're not quite ready to say that the beams are colliding at our experiment, but they probably will get there in a few minutes. So very fun. Do you want to say anything about the result, or? So on your Facebook page,
Yeah,
it's nice.
You click
on that? I think it's, yeah, BBC.
Yeah, so we had this announcement on Tuesday. They got a lot of press coverage.
So that's what the exciting events look like.
Yeah, so that's one of the sorts of collisions they were
So
talking
2
about.
protons hit each other, and about 1,000 particles are coming out on that event, which is pretty exciting. It happens, but what was unexpected is not that there were 1,000 particles, but this is the plot. There's always the money plot, as we say. What is the plot that shows the interesting thing? So there it is.
And what people don't understand in this is there's a ridge here that isn't theoretically predicted in this distribution.
So you expect to see the spike at 0 and 0 on the 2 axes there, because that's where particles come out, and there are other particles nearby. That's what we call a jet. That's expected. And the one that appears separated in phi, which is the azimuthal angle, is appearing on the other side of the event, so to speak, because momentum is conserved. If you have a jet going in one direction, you better have something going the other direction to balance momentum, because the 2 beams come and hit head-on. There's no momentum in the plane transverse to the beam in the initial conditions. The final state better have something going in the other direction. So that's the ridge, the big fat mountain peak on the upper part of the plot. But the fact that there's also a peak along at phi, delta phi equals 0 is not expected.
So this isn't expected. Some conjecture that we're making a new phase of matter. Some quark-gluon plasma, and there's something else going on. So that came out this week, and it's an example of the first thing that's come out of the LHC that's never been seen before.
So something like this has been seen when you collide 2 nuclei together at the Brookhaven lab. But it's not clear yet what that is due to, and it's not clear what this is due to. They might be related. They probably are related, but we don't know yet.
What were the energies of compared to this?
So the energies are, hundreds of GeV. I forget how many hundreds, but they're colliding nuclei. So you have, so if you collide gold on gold, you have a lot of nuclei, and so you expect, collective behavior effects and that to go on. Here we're just colliding protons, and yet it looks like we're making some sort of quark-gluon plasma or something. That's surprised people.
So this is what's called a correlation function, and this is saying that if you look in an event at the same angle, you're more likely to find another particle when the difference in phi is 0. The plot, the predicted plot, just has a big spike near delta eta, also of 0, but not this original part. And that spike is actually chopped off. But this is really real. We can see it. I don't know why it's there. And that could happen when you collide 2 nuclei together. You have all kinds of particles produced, and you could have a new phase of matter. It's like melting an ice cube, or maybe better, boiling something. And you have a plasma, ionized particles. You have now, with the strong force being the issue here, is that we're entering a new phase. The strong interactions, the phase is governing the phase transitions here. And we don't know what the conditions are like when you get high enough energy density. And in the proton-proton collisions, we're probing a similar energy density as you would at lower energies for the nuclei colliding, because there are just more particles in the nucleus, and they're tightly packed. So it may be related, probably is, but if you draw a phase diagram for pressure or density of particles, you'd be in a different place. And so that's why this is interesting. It's just, if we see something funny, heavy ion collisions, we might be seeing something related here, and we'll map out the diagram by actually not work that Dr. Padley or I do. We're more interested in the particle physics you can do. But the LHC will also run with gold nuclei later this fall. And of course, this probably a study like this will be of prime interest to see what happens. And there, the energies will be much higher than Brookhaven. So again, move to some other part of the phase diagram. So just like water can have, you can have vapor, and you can have solids, and you can have liquids. And there's even a magic pressure and temperature where you can have all three at the same time. We may have found a new phase of matter here, which is not the primary reason most of us are involved in the LHC. We're looking for new physics at the microscope, the tiniest level, not some collective effect. But this is pretty cool, and the completely complementary physics-wise. I mean, you can do the same experiment, the same data. Just you're picking different events.
So the CERN theorist John Ellis put it well once. He said, and actually Margaret Thatcher asked him, what do you do? And he says, I make predictions so that people can go build experiments and look for what I predict, and then find something completely unexpected. And that's actually what's most interesting. Usually how progress gets made, regardless of what you think, right? So I don't. If you had asked us a year ago, we would never have anticipated something like this showing up.
And even if you had, you would have said it would have been in the gold collisions, not the proton-proton collisions, right? So, but this happened first. I mean, they ran the protons first, so wait for gold. Maybe something more bizarre will happen.
Well, so more along the particle physics line, I guess the big question that everybody wants to know is what's the time scale, and what can we hope to, when can we hope to see evidence of the Higgs, and when is it going to actually be possible?
So the Higgs is hard. So the Higgs takes a long time. What's coming out now is we're already testing, you've seen books by Lisa Randall and all these people talking about extra dimensions and things. And we're actually starting to challenge those theories. So the first results challenging those theories are coming out.